All right, guys, how you doing? This is Coach Scott, and let's do a little quick review of Unit 6 so you guys will be prepared for any type of quiz or test that we'll be having on this subject very shortly. So again, um, Unit 6, let's break it down to the meat. All right, we studied one, the Bohr model. The second thing we covered was the quantum model and the quantum mechanics. It's sort of, or that is the basis of it. Then we talked about orbital diagrams and E configurations. Okay. And I think y'all got that pretty good, but we'll mention them real quick on this video. So let's think about one, the Rutherford model. This is what I've got drawn here. The Rutherford model, you had a very positive nucleus. That's where the protons were, right? And then in a set orbit, like the moon and the sun and the earth, or the earth and the sun and Mercury and the sun, so on and so forth, they'd go in elliptical orbits around the nucleus. There's a problem with that. One, um, you got a positive proton nucleus and a negative electron. Where's the problem there? Well, by traditional physics, they should be attracted to each other and they would eventually crash and go away. Now, if you want to get specific, that's the Coulomb's law. And we'll talk about that later. That's an issue. And then also think about it, atoms don't produce light. All right. And those that do will only do it at certain wavelengths. And the Bohr model explained this, okay, that these electrons are in stable orbits, but when they absorb energy, they can get excited and go up to a different orbit. And then they're going to go back down to the stable orbit, all right? And they're going to fall into that little lower energy orbit. And when they do, they would emit light at those wavelengths. And it would be depend upon the distance that orbit was from the ground state. So those are some differences between and an improvement on the Rutherford model, the traditional nuclear model, and the Bohr model. Now the Bohr model, it didn't last very long. Okay, and when we got into quantum mechanics, we saw that the Bohr model really didn't fit everything other than the hydrogen atom. All right, so the quantum model allows the electrons to have both wave and particle properties. All right, we found that through the double slit experiment, and it allows us to understand electrons, how they behave, um, how most of the electrons behave, rather than the behavior of a specific electron. All right, because we probably know where they're at. Okay, so let's talk about some of the math. Let's continue on with our the Bohr model and add to that. Okay, so what's the frequency? We got some math here we've got, right? And we've got those two formulas, and they're on your formula sheets. The first one is lambda equals hc, which is Planck's constant, and c is the speed of light, over the change in energy, delta E. All right. So another one we have is c is equal to lambda, the wavelength of the light, times the frequency of the light wave. So if we know wavelength, we can calculate frequency because well, we know what the speed of light is. So let's think about that. If I've got a wavelength and it's a very long wave, and let's say it has a wavelength of 2.5 meters, all right, this is an example, 2.5 meters, that equals lambda. Well, that's cool. Whoop, bad lambda. But everything we do is in nanometers, so I have to calculate that or I have to convert it. And the best way to do it, we'll do it here. If I know that there's a billion nanometers, 1 times 10 to the nanometers in 1 meter, right? So if I want to convert to nanometers, okay, in 1 meter, there's 2.5, or there's, well, a billion nanometers. So if I take 2.5, okay, and I divide it by 1 times 10 to the ninth, I come up with, something that doesn't work like we normally do. 2.5 times 10 to the minus ninth. 2.5 times 10 to the minus ninth. So because I did that, because I divided that, right? All right. Wrong way. 2.5 times, that's meters. So in 1 meter, is 1 times 10 to the ninth nanometers. And I get 2.5 times 10 to the minus ninth nanometers. So if I got that, I know C, I'm trying to find frequency. So if I know frequency, then I know C is divided by the lambda. I know lambda now. I know C. So that would be what? 3.0 or 2.998 or whatever it says times 10 to the 8th meters. Oh, I messed up. I didn't have to convert anything. I know what it is in meters, and that's if they gave me in nanometers, I'd have to convert it. So now I know that it's 2.5 meters. So what's the wavelength? All right. 3.8 divided by 2.5. So my frequency would be, I don't have a scientific notation, 120 or 1.2 times 10 to the 1 times 10 to the what, eighth? 1, 2, 3, 6, 7, 8. Yeah, it would be 1.2 times 10 to the eighth hertz, or reciprocal seconds. AZ, or 1 over seconds. Okay, and that's how I find my frequency. If I've got it in meters, I don't have to change it. It's only if it's in nanometers. Let's look at one of those. All right, so let's say, for instance, that I've got a lambda, and this is in nanometers, is 200, 225 nanometers. And the question is, what's the energy? Well, I'm going to use that other equation. All right, and let's see. So lambda is equal to hc over delta E. Well, I don't know delta E, it's asking for it. I know lambda, I know H, I know C. So I'm going to use my algebra and I'm going to make this for me HC as an H over lambda. All right, so H, if I look on the back of my sheet, H is 6.63 times 10 to the minus 4, 34 joules seconds, times, I'm going to use what they say here, 2.998 times 10 to the 8th meters per second. And I'm going to convert that to meters. So I divide 224 nanometers by 1 billion, and I come up with 2.25 times 10 to the minus 7th meters. So now I've got to use my calculator. And I put it in the calculator. Give me a second. It's 34 times 2.998 divided by 2.25 double E minus 7. And I come up with, this makes sense, an energy of 8.83 times 10 to the minus times 10 to the minus 19th joules. Not a lot of energy, but enough. All right, so I can find delta E if I have lambda. I can find frequency if I have lambda. Let's look at another one. What is the energy of a photon? Oh, no, I did that one. Okay, so that's really all the math we're going to need to know. Again, now let's go on to the quantum world. Quantum. All right, and what do we talk about in the quantum world? Well, in the quantum world, let's see. It all started with the double slit experiment, and we noticed that the electron didn't act. It acted like a wave, but it also acted like a particle. So we call that the wave particle duality, right? Where the electron would split as they go through there and it would act like a wave instead of acting like a particle and just forming two little deep dark circles. It acted more like a water wave or a sound wave. Okay. So the double slit experiment was that experiment that we really got to thinking about that. Now, let's talk about quantum numbers. And again, what do you need to know? All right, so there are 4 quantum numbers, and you need to know the first one, n. N stands for the principal quantum number. All right, and that's the main orbital that the electron could be found on. Again, you need 4 quantum numbers to identify an electron. It's sort of like an address, right? Then the next one is the L, which is angular. Angular. Okay. Now, there are 4 angular numbers, are shapes. You have an S shape. We talked about those. You have a P shape, a D shape, and F shapes. So those are the shapes. S, P, D, and F. That's what you need to know. Now, if you're going to put a number to that, the S's are zeros, the P's are ones, these are two, and F's are three. Okay, there's only 4 of those right now. The next quantum number is the ML number, and that is the magnetic number. I don't know why they call it magnetic. I'm not a physicist. Okay, and that's the orientation in space. Okay, the magnetic orientation number. Think about it like that. Are they along the XYZ coordinate or wherever they're at, right? And there's one of those for the S, a sphere. This is the only thing it can be. There's 3 for the P's, 5 for the D's, 7 for the F's. Okay. So the S can only have 0. The P's, the number would be -1, 0, or 1. The D's can be -2, 1, 0, 1, R2. You see a pattern there? And the F's, yes, -3, -2, -1, 0, 1, 2, R3. Now, if a level, a principal number, can only have one orbital, like 1, it's going to be 1, 0, 0, and then of course, the MS number. We'll talk about that in a minute. All right. So those are the different orientations, the magnetic orientations. All right. So the angular number, okay, the S is always going to be 0. And of course, there's 0 there too because there's only one. The P's will be 1. The D's would be 2. And the 3 would be, or the F would be 3. And we'll do some practice. The last quantum number, and again, how many quantum numbers do you need to identify a specific electron? You need 4, 4, 4, 4, 4. The spin number, okay? And each orbital will only have 2 of these. This is the spin number, all right? Because for an electron, this is Hund's rule, or no, the other one. You can only have 2 electrons in an orbital. And if you do have 2 electrons, they can't have the same spin. So one of them will flip and go to the opposite spin. The two numbers there would be plus 1/2 or minus 1/2. So if I was to put a quantum number like so, 2, 1, 0, plus 1/2. What does that mean? The first one, the principal number, that means it's on the second level. It's on the second energy level. The second number, the 1, means it's a p orbital. The third number, okay, the third number means that it's 0, so it's a p orbital, so that means it's this one right here. All right, it's in one of those shapes. It means the -1 or the 1s are probably already filled, but it can start there. It can start any of those. And then the last one means it's got a positive spin. What's the difference with that? With a negative spin, there's not. It's got a different spin than the other one that may be in that orbital. So this is the address of a second level p orbital, okay, with that shape, the 0 shape, and that spin. That's all you need to know about quantum numbers. What you really need to know is that there's 4 quantum numbers are needed to identify a particular electron. That's all. We got another page here. So we can draw some more. Okay, cool. Now what you need to know that for quantum numbers. Now for most of what we're doing, and really this is electron configuration, you know that there's 3 p's in the second level, right? You need to know how to write electron configurations. And really that's what you need to know after here. Okay. So let's talk about econfigs. Know that you're going to, let me see if I can't put some of my cool charts there because I want to. It makes life easier for me. Let me put one right there. Paste. All right, I did. All right, so let's do econfigs. Okay, so if I'm asked to write a configuration, okay, and that's one of those things up there, that means it wants me to follow the three rules: the off-bow rule, Hund's rule, and Pauli exclusion principle. Okay, so whenever they ask me to write an econfig for a element, let's pick one. I'm going to pick scandium, number 21. First of all, we have to figure out how many electrons. How to do that? I look at a periodic table and I'm looking for scandium, Sc. And I see that it has 21 electrons. Okay, so now I'm going to start writing my configuration. I got 21 electrons I got to fill up. There's one, there's two. And again, start from the bottom. Starting from the bottom is what? The Aufbau principle. There's three, there's four, five. Oh, and then I have to go to the Hund's rule. I'm going to fill up this one next. 6, 7. Oh, and I'm going to follow the Pauli exclusion principle, and that each of these electrons have to have a different spin. So I'm up to 10 now. 11. I keep going up. 12, 13, 14, 15, 16, 17, 18, 19, and 20. I'm getting close. 20, and then there's my 21. So now, after I've drawn that, I should be able to write the electron configuration. And it would be, well, pretty simple. 1s1, or 1s2 rather, subscript, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d1. Wow, that's it. Now, if you start looking at it like that and break it down, well, we covered a lot of stuff, but did we really? Okay. Breaking it down, there's not that much you got to know, right? Bohr, what's happening? His model, the electron is falling to a lower energy state after it got excited up, and it's emitting a photon at a certain wavelength. That's where the colors come from. All right. Blue flame, uh, blue has got more energy. All right, which means there's it's going. Blue is more energy than red. All right. So if you got a blue flame and something has a red flame, then there's more distance for the blue one to fall. It takes more energy or puts out more energy. All right. Quantum, can we exactly know where an electron is? No, that's according to Schrodinger. We can only know the probable location of it. All right. Make sure we know how to do Hund's rule. Make sure we know Pauli exclusion principle, and we know the off-bow diagram. Make sure we know how to do electron configurations. If we have to, draw an orbital diagram. You got plenty of them. All right. How many elements can have the same ground state configuration? There's only none. They each have a different electron configuration. Okay. Know that the S subshell can only have one orientation. It can only hold two electrons. The P's, there's three. The D's, there's five. And the F's are seven. So the P's can only have 6 electrons. The D's can only have 10. And the F's can only have 14. All right, know what the different, again, just know what they are. The N, the L, the ML, and the MS number. What do these mean? All right. Anyway, I think you guys can do well. Know where these things are at on the periodic table. Know how to find where the S2 configurations are. We looked at those at the very end. Um, yeah. So guys, I think you're pretty well squared away for this, and it's just a matter of doing well, and you guys can do it. So anyway, this is Coach Scott saying, "Hullabaloo, connect, connect."